Hello and welcome to another amazing video lecture. Today's lecture should be an interesting one, and I'll try to make it quick as usual, but we'll see how that works out. So today's on the formation of the universe, galaxies, and Earth. So we are starting a new unit, this unit is going to be really focused on the Earth. So we want to start with, how did the Earth form? So let's take a look. So be really careful to not write everything down. I'll kind of write circle things that I feel that you should write down. So if you can see this little picture on the left, this is the beginning of the universe at the bottom, and where we're at kind of today is towards the top. And yeah, so basically, the universe began with a hot explosion called the Big Bang. The aftermath of the Big Bang consisted mostly of radiation, but as things cooled, the elements hydrogen and helium formed. Okay, so really, all you should write from this page is, is this part kind of up here that we know. Hopefully, most of you kind of know this already. It started from just pure energy that took up a very small amount of space, and then expanded, and it's still expanding. So this is a cool another picture. Obviously, don't write any of this down. This is just to help you guys kind of see. I know there's a lot going on here. So basically, if this is the beginning of time over here, okay, then basically at time t minus 43 seconds, that's a really, really small amount of time, much smaller than we can comprehend. Things were really hot and just pure energy. And then as we got to, you can see 10 to the minus second, we already have a lot of things going on. So don't worry too much about this stuff up here. I'm not going to test you on it, but if you remember protons, so in this way, protons are forming hydrogen atoms and then helium atoms. And if you notice anything on the periodic table, those are the smallest elements. So in the beginning of the universe, the smallest elements were formed first, and as things cooled off. So one thing I do want you to know is that as time increases, things do tend to spread out and cool off. Okay? And so as that happened, elements started forming bigger and bigger elements into what we see today with the elements we know today. So definitely don't write all this down. In fact, don't write most of it down. Let's just kind of go through some of the major parts. So what is the evidence for this? So some of you know this is probably a controversial, not in science, but if you, in other parts of your life, this may be a controversial idea, the Big Bang Theory. But there is a lot of evidence for it, and that's why we teach it, but it is still a theory, so it's always being questioned and tested and everything. It's not a law. But we do teach it because there is so much evidence. So first of all, we are reasonably certain that the universe had a beginning. The galaxies appear to be moving away from us at speeds proportional to their distance. So that's important. Write that down. That's a big part of evidence. Galaxies are moving away from us at speeds that are proportional to their distance. So this is, you might have heard of the Hubble telescope. So this is what we see when we look through a telescope out at deep space. So this supports the expansion of the universe and suggests the universe was once compacted. Third, if the universe was initially very, very hot, as the Big Bang suggests, we should be able to find some remnant of this heat. And in 1965, this was discovered. So we did find this kind of, there's this microwave background. So when you turn on, actually I learned this, when you turn on your TV and there's a bunch of static, what you're actually seeing in that static, or part of that static, a percentage of that static is microwave background, and that's actually, that cosmic microwave background is another piece of evidence. And you see that whenever you see static, there's a little part of that is in there. So that was discovered. So there's remnants of this super hot flash that happened. And then finally, the abundance of the light elements, hydrogen and helium, found in the observable universe are thought to support the Big Bang models of origin. So the light elements, helium and hydrogen, are found most abundant in the universe, and that makes sense because they were the first and easiest to form. Let's keep moving. So as things started expanding, nebulas were formed. So a nebula, you do need to know, is a cloud in space. It's made of gases and dust. So as more and more elements were formed, they started to form together and created gas and dust, different kinds. And nebulas are the birthplace of stars. So most of the ones we see are inside our Milky Way galaxy. So this is how we believe our solar system was formed and eventually Earth. So remember, we're trying to get to how is Earth formed. So the solar nebula theory is is the basis of modern theory of planet formation. Planets form at the same time from the same cloud as the star. So you do need to know a little bit about this. So planets form, so I write this down. Planets form at the same time from the same cloud as the star. Planet formation sites observed today as dust disks of Tauri stars, sun in our solar. So don't worry about any of this stuff right here. Basically, the picture is probably a little bit better. So you have this giant nebula dust cloud, and eventually that dust cloud starts to compact and is spinning still from the Big Bang. And where the most mass forms, you get a sun. And then as you start to get little pockets of other pieces of mass forming, you start to get planets. And all the while they're still spinning like a big blender, kind of. So this is how we think our universe. So that's why we see solar systems that kind of move in this flat way. They're not going all over the place. They're kind of moving in a flat place. So planets grow from gas and dust in the disk and are left behind when the disk clears. So why do they form this way? Well, Newton was kind of the first guy to figure this out. And it has to do with gravity. Okay, so we're going to spend a little bit of time talking about gravity. So, through Newton's observations and experiments, I'm sure you've heard of the famous apple falling on his head, he reasoned that the strength of the gravitational force is not constant. So in fact, the magnitude of the force is inversely proportional to the square of the distance between the objects. So let's not write any of this down, but basically what he's saying here is that gravity is not constant throughout the universe. It's different depending on what you're observing. So everything, all matter, so this is what you do want to write down, exerts a gravitational pull or force. And what he's saying here is that that pull or force is based on two things. It's based on how much matter there is and how much distance there is between the objects that you're looking at. So when we look at gravity, we're always looking at the pull between one object on another object. So Newton found that gravity was a universal force acting between any two objects. So I kind of already stated that, so make sure you understand this. So the Earth pulling on an apple, or you, or the moon, those are all gravitational forces between two objects, or two pieces of matter. So this is something you guys need to understand. One number, it's a constant, you're going to have to memorize and write it down, is going to be the gravitational force on the surface of Earth. So this is unique to the surface of Earth. It's 9.8 meters per second squared. And take a look at those units. So does anybody know what those units might account for? Meters per second squared. Well, if you don't know, this is an acceleration. And it's a number you need to remember. Okay? And we're not going to do anything. Don't write anything else down. Just write down this is the gravitational constant on the surface of Earth. This will be different if you go to different planets or different places in the solar system, or even if you go higher in Earth's atmosphere or even beneath the crust. This may change. So this is only at the surface of the Earth. So let's talk about this really quick and break it down. This sounds really confusing, but hopefully it'll make sense once I explain it. So Newton concluded that the gravitational force is directly proportional to the masses of both objects you're looking at. So remember, gravity is always between two objects, and inversely proportional to the distance between the two objects. So all this fancy jargon means is when something, and you do need to know this, when something is directly proportional to something else, that means that as one goes up, the other one goes up. So if the mass of an object goes up, either object, then the gravitational force between the two objects will go up. So if it's between Earth and me, and I get bigger, then yeah, the gravitational force will get a little bit bigger. I mean, when it's something as small as a human, it's almost impossible to detect. It's very, very small, but it will go up. Now, here's the other thing. When something is inversely proportional, these are mathematical terms, so I can understand why you guys are confused, but let's just understand it now. It's really not that hard. So let's take, and I'm going to give you an equation that demonstrates this, but basically, if they're inversely proportional to the distance between two objects, then as one goes up, and this is distance, so the other one was mass. As mass goes up, then the gravitational force goes up. As distance increases, what do you think happens to the gravitational force if they're inversely proportional? Well, if you guessed the gravitational force goes down, then you were correct. So in this case, inversely proportional means that as one goes up, the other one goes down. And so in this case, as distance between two objects increases, the gravitational force decreases. And this makes sense, or else Earth would be pulling on everything in the universe equally. But it doesn't. Earth does not pull on Jupiter as hard as it pulls on the moon, correct? So, and that's why as we get further, and if you know anything about space travel, as we get further from Earth, we can escape its gravitational pull. So, I'm not going to have you understand this equation. I want you to understand the last slide more. But this is just to kind of show you the mathematical representation of what we were talking about. So this is what's called Newton's law of universal gravitation. I won't spend too much time on it. But basically, somebody figured out a long time ago this constant. I'm not going to have you memorize that, so don't worry about it. But basically, if you want to know the force of any two objects, and this equation is kind of weird, but if you want to know the gravitational force, that's how we would write it, between any two objects, it's big G, which is this number, and again, you don't really need to write this down, it's just for your understanding, times the mass of one object squared, the mass of the object 1 times the mass of object 2 over the radius or distance between the two objects, okay? And so if some of you guys are looking at this really confused, let's just take a second to break this down. Let's just say that when you multiply big M times little m, you get 1. Okay, so let's just say that 1 is there. So the mass is kept constant. What will happen to the and this is kept constant, so we can deal with that. What do you think will happen to the force of gravity if we increase the radius between the two objects? Well, let's say the radius was 2 at first, but we increased it to 4. So now, if r is 1 over 2 to start with, and then it goes to 1 over 4, that means that the gravitational force, so at first the gravitational force was 1/2, and then we increased the radius to 1/4. The gravitational pull is now smaller, right? 1/4 is smaller than 1/2. But let's say we now keep this r constant at 2, but we increase the mass of either of these two at 2. Well, now 2 over 2 is 1. The gravitational force is higher, but what if we increase it to 4? If we increase the mass to 4, now it's 2. 4 divided by 2, so it went up. And that goes exactly with what I was talking about before. This is an equation that is directly proportional with the mass and inversely proportional with the radius or the distance. Okay, so that's mathematically how it looks. The gravitational field. So gravitational fields are created by very large objects. Well, all objects, but we only sense them when the object is really massive. So basically what I want you to think of this is an invisible disturbance in the space around them. So the way we think about this is if you have a trampoline, okay, let's just say this is my bad drawing of a trampoline, and you put a golf ball in the center, okay, and you spin some marbles in a circle around it, they'll kind of eventually come to the middle, right, after a while. But let's say you take that same trampoline and you put a bowling ball a little bit more massive, right? It's going to pull the trampoline down further, so when you try to spin those marbles, they're going to move to the center really fast. So this is how you can think of this. Things that are really massive disturbs the space around them. Just as this golf ball will disturb the trampoline a little bit, but the bowling ball will disturb it a lot and pull it much further down. This is why if you ever have a friend who, let's say, is really big and muscular and they sit at the middle of the trampoline, they're going to pull a lot more people towards them. This is how gravity works, and they think it's because it alters the actual fabric of space around them. So that's a really interesting, I think, pretty neat concept. So, Newton's law of universal gravitation is also called the inverse square law. You don't really need to know that, so don't write anything down. We'll just kind of... This is one equation I want you to know, okay? So we already defined what g is. If you remember, it is 9.8 meters per second squared, and that is a unit of acceleration. So if we take that and we multiply it by something's mass here, then you get the gravitational force. So we will actually be doing some problems where we use this equation. So make sure you write this whole thing down. It's easy just to write it F equals mg, where F is the gravitational force, right? So gravity, the force of gravity. And m is the mass. And g is 9.8. Okay, so in this problem, I may have you solve a couple simple problems like this, but this makes sense, right? Because what happens if you increase the mass? What happens to the gravitational force? Well, it goes up, right? And what happens if you decrease the mass? So this is obviously where distance is kept the same, right? If we're not doing anything with distance or anything, because that would also change gravitational force. For us, this is basically what we use on Earth, on the surface of Earth, right? This is the gravitational force on Earth. So if I throw a baseball up, that baseball is going to be pulled down with the gravitational force of whatever its mass is times its gravity. So we're going to practice some of those at some point. Okay, so what does this have to do with what we were talking about before? Well, basically we're trying to answer why do these planets form from this giant gas and dust nebula? Well, what happens is the solar nebula, eventually it's just made of so much dust and gas that gas and dust starts to bounce into each other and basically start to form bigger and bigger chunks. And as those chunks grow bigger, they get more gravitational pull. So they start to pull in more chunks. And we'll talk about what this is called in a separate lecture. But basically, you get your sun, which is the most massive and has the biggest gravitational pull at the center, because that's where most of the mass and the gas and dust started to kind of stick together. Whereas the planets on the outside have less mass because they didn't pull in as much mass and matter, I should say. So don't really write any of this down. Just understand why it's important to... what I would write for this slide is basically that the solar... Actually, you can write this down. Let's write this down. And remember, it's because of gravity. And now we know what gravity is. And sorry if you can't really... That was kind of bad. It's because of gravity, right? Why do the solar nebula contract and flatten into spinning disks? It's because of gravity. And this is also why the planets continue to spin around the sun today, because they're pulled in by the sun's gravity. So, from the Big Bang Theory, we created all matter and energy that exists in the universe. And it's still there in our universe. It's just moving out. The universe is just continuing to expand, and the energy is continuing to move around. So the solar nebula theory uses that matter and energy to create galaxies and solar systems and planets, and eventually planets. So you do need to write this down. Let's not write this down. Let's write the bottom part down. That's the more important one. So lastly, we know that these create galaxies, right? So those solar nebulas are forming our solar system. So what is a galaxy? So a galaxy is a large group of stars, which is like our sun, outside of our own Milky Way. So a galaxy is made of a billions and trillions of stars, each that have probably their own planets around them. So galaxies are made up of a lot of solar systems. So galaxies are made up of millions and billions of trillions of stars and solar system, which means solar systems. So our galaxy, and our galaxy is the Milky Way. It has about 200 billion stars and lots of gas and dust. It is a barred spiral, so you can actually see it on a really nice night if you're not around a lot of light. About 100,000 light years wide. So that means it takes light 100,000 years to travel across. Our sun is halfway to the edge, revolving at 500,000 miles. So it takes our solar system about 200 million years to revolve once around our galaxy. So think about that. We have our planets that take a year to revolve around our sun, but then our sun and our solar system is revolving around this giant galaxy that takes 200 million years. And you don't really have to write any of this down. It's just kind of interesting. But you do need to know that we live in the Milky Way galaxy, what a galaxy is, what it's made of. So you kind of want to understand that planets are part of solar systems. That's what I would write down. Planets are part of solar systems make up galaxies. And then the galaxies make up the rest of the universe. So here is our Milky Way. So if you were to zoom out, and how astronomers do all this and figure this out is crazy. It's mind-boggling. But anyway, that's our lecture today. Sorry it was a little bit longer, but pretty interesting stuff. Make sure you guys understand the gravity stuff, and we'll practice with that equation in the next couple days. Okay, bye.